Hello and welcome to Chemistry with Dave Hicks. Today we're going to talk about gas laws, specifically the ideal gas law, and I'm going to be working on this from a perspective of an IB student. And the units will look a little funny to you. However, the concepts are all the same. Our goals here today is to know the formulas and the units associated with the ideal gas law, and to get around to calculating some answers to gas law problems. Now, it all kind of starts with Avogadro. He had a law that said equal volumes of gases at the same temperature and pressure have an equal number of particles in them. And with this, they connected all gases together so that we can work with any gas. They connected it to the mole because this is the way we eventually started counting the molecules that were out there. And eventually this got connected to what we would call a universal constant. And that constant became part of what we would call the ideal gas law. There's the ideal gas law for you, PV equals nRT. Let's see how we use it. First, we need to address some units here, SI units specifically. And so the IB likes to work in SI units. So for pressure, we're going to be using the unit of Pascal. It's kind of a physics unit, so there's another little part that I'll share with you explaining this and how it fits in with the ideal gas law. You may also see it as a kilopascal because the pascal is kind of a very small unit, which turns into very large numbers. Our standard is 100 kilopascals, which is standard pressure, like you may have seen in standard temperature and pressure, 100 kilopascals. Volume has to be some derivative of meters cubed. You know, the SI unit of length is the meter, and volume is length times width times height. So that turns into meters cubed. That's a little unusual. However, decimeters cubed is similar to a more familiar unit, the liter, and cubic centimeters is more like the milliliter. In fact, it is the milliliter by definition. Temperature has to be in Kelvin. So this is maybe one of the top mistakes for these types of problems is that students forget to change their temperatures into Kelvin. Ultimately, these SI units have to match the universal gas constant being used. And for IB, we're going to use our specific gas constant. If you are watching this because you are working in some other class that is not using units like this, then all you have to do is just make sure that your units for pressure, volume, and temperature match with the units that you're using for your universal gas constant. Speaking of the universal gas constant, here's what we're going to be using, 8.31 joules per mole per Kelvin. When we put the -1 exponent up there, it means divided by, right? That's from math class. And so joules per mole per Kelvin. Now, a Pascal, which was our unit for pressure, is equal to a joule per meter cubed. So you can kind of see where the units for pressure comes from, Pascal, and where the units for volume comes from, the meter cubed, and how it sort of connects with this unit called the joule. So if you are going to set this up with SI units using the 8.31 joules per mole per Kelvin, then you have to use your units in pascals for pressure, meters cubed for volume, Kelvin for temperature, and of course the mole for the number of molecules or particles present. So let's work on some examples, eh? So in this one, it says how many moles of nitrogen gas are going to occupy a volume of 5 cubic decimeters 99 kilopascals, and 22 degrees C. When I took chemistry, I had a great chemistry teacher. His name was Arthur Logan. And I can even remember where I sat in his room when we talked about gas laws. And the thing that he made us do is he made us write down the side of our paper the letters for the ideal gas law. So he would have us write PVNRT, and that's the way we started our problem. So I've been sharing this with students all along ever since that time. So thank you, Arthur Logan. So this just helps me set everything up and get all of my numbers in the right place. So I'm going to look around for pressure, and I see, okay, 99 kilopascals. And then I'm going to look around for, well, I'm going to stop here. I'm going to say, hey, you know, that's 99 kilopascals, but I need it in pascals, right? So 99 kilopascals is the same thing as saying 99,000 pascals, right? Because a kilo is 1,000. For volume, I see that it is 5 decimeters cubed. And I know that a decimeter cubed is, I have to get it into meters cubed, so that's going to be 0.005 decimeters, or excuse me, meters cubed. And N is what I'm solving for, so I like to put a question mark there. R, I'm going to use my universal gas law constant. I'm not going to write out all the units just because I'm trying to save some time here, but that's joules per mole per Kelvin, right? And then temperature here is 22 degrees C, and I know that I have to add 273 to that, and when I do that, that makes it 295 K. Whoops, scribble that out, 295 K. There we go. So now that we got all of our numbers organized, all in the right unit, and that's what I use this little chart for on the side of my paper that I've created here. Now I can lay down the law, right? In this case, the ideal gas law. So PV equals nRT is the law. And I can start substituting things in. 99,000. Oops, excuse me. 99,000 for this, times 0.005 for that, equals N times 8.31 and times 295. I'm not using units there, again, to save a little time and a little space on my screen, but you can get the units from the side here. And then finally, I'm solving for the number of moles. You can do this however you want. I like to solve with letters first and then put it into my calculator all at once. But however you feel most comfortable doing the algebra with this. In the end, I ended up with 0.202, and this is moles of nitrogen gas. There we go. So recapping, I make this little chart right here so that I can organize all of my variables and get them into the right units. And then I lay down the law and put it into the ideal gas law formula and solve for it. Just a quick note, some of you smart math people out there may have realized that, hey, I'm multiplying this one by 1,000 and dividing that one by 1,000, so that's going to cancel itself out, which is true. And if you want to work like that, you can. But since we're being all proper with using the SI units, I'm going to be proper and convert them to the correct units before I put it in there. All right, let's try another example. Another very common way that we use this is we want to know what volumes will we get from a reaction, right? So in the end, I have this volume. I want to know what volume is it going to occupy. Many times I start with a volume. I want to know how many moles it is. And then when I have moles, I want to figure out, well, what volume would that turn into? So these are very commonly used amongst chemistry problem circles, I guess. So for this one, again, starting out, make my chart down the side. Pressure was given to me. I'm not going to go through the process of showing you how to convert it this time. I'm just going to go straight to my correct number. That'd be 235,000 pascals, because it was kilopascals, right? And volume's what I'm looking for here. Moles was given to us this time, 1.25 moles. R, not going to write my units for that, but we know it's 8.31 joules per mole Kelvin. And temperature, I have to add 273 to 75. And when I do that, I get 348 Kelvin. Now I'll write out the ideal gas law here. And after I do that, I'll plug in my numbers. So this is 235,000 times V is equal to 1.25 times 8.31 and times 348. So again, solve that however you want. In the end, I got 0.0154 meters cubed, but we said we wanted this volume in decimeters cubed, so I could convert it, and that would be 15.4 decimeters cubed, because a decimeter cubed is 1,000 times the meters cubed, right? Okay. So how are we doing? I've shown you two great examples. Again, the idea is set up your variables, get them in the right units that will match our universal gas constant, plug it into the law, and we've got ourselves an answer. So here's a couple for you to try. The great thing about video is that you can hit pause and work through these two problems, and then in a minute, when you're done with them, hit play again, and I will go over the answers. So go ahead, hit that pause button, and when you're done, come back and check out the answers. Okay, how'd you do? Here's my answers. I've got, for the first problem, we're checking out how many moles, right? So I didn't set up my little chart along the side, but hopefully you did, PV and RT, and you converted the 95 kilopascals into pascals, right? And you converted the decimeters cubed into meters cubed, and you changed the degree C into Kelvin. Solving for N, I got 0.191 moles out of that. Sometimes people have issues with this being Cl2 like that, and they think that they need to do something with that. But, you know, this is for all gases, right? We said that in the beginning, that Avogadro said all gases will work this way. So in this case, it's a molecule of a gas, and we don't have to necessarily do anything to it. That's just his formula. All right, and for the second problem here, it's again you set up your PV nRT down the side, and hopefully you changed your degrees C into Kelvin. This was already in meters cubed, so we can leave that alone. And when you put the formula and the law together using your ideal gas constant, I ended up with 123,819 pascals. Remember, your unit's going to end up in the proper unit that comes from your ideal gas constant, which is pascals. And so if I want to change that to kilopascals, which is what we normally work in because of its smaller numbers, and in this case, I only had 2 sig figs, so that works its way out to 120 kilopascals. Okay, I hope you enjoyed this tutorial on how to do ideal gas law problems using IB units, and I wish you luck with your chemistry. Have fun and see you next time.